Okay, thank you for coming again and not being scared of the course. So we are completing the theoretical part for ionic motion, or at least postponing it for a good dozen of lectures, and we will focus on actual electronic structure, which is referred to as computational chemistry by many authors. So many books actually start presenting their material from electronic part and forget completely about ionic part or leave it for later things. So organizationally, I was uploading a couple of handouts which are not required at any rate. Just if you have nothing to do and you want to entertain yourself, you can look on them on D2L and just enjoy. So there are some notes on geometry optimization. There is a biography of one developer of the basics for electronic structure theory, and there is a version of lecture number 9 from 3 semesters ago, where there was a Dr. Mikhailov who was substituting me when I was going to lectures, and you can see an alternative way to present things. So I have also composed a little homework which is identical to last 3 slides of our previous lecture. I'm just suggesting that you repeat the same table, pretending that you are computers and finding optimum of some function. Shouldn't take long. And also, I know that there are schedule conflicts for some of us to visit those arts and science labs. And when we were visiting them, I was trying to take notes, pretending that I'm doing this lab myself, and those notes are also available on D2L. Just if you want to check if you were doing the right things, or if you were not able to attend and you want to see what was there. And so just feel free to look on it. So here are the subjects that we are going to attempt to cover. We are completing the geometry optimization, but we do know that during optimization we were using some black box, or practically when we were running Gaussian, there were some portion of our process that does solve electronic problem. We do not know how, but we want to know it. It is basically what we are going to do. Okay, here is this one of the handouts that you can download just to bring a little human factor to boring lectures. And some of you are traveling to a conference that known Sunnybell Symposium. So this person was actually also attending it. Well, unfortunately he died there, but anyway, big people were attending this conference and this island. And he also was a part of the team of University of Florida Quantum Theory Project that is organizing this symposium. So we are approaching very core of computational chemistry by talking to those people. So if you do not get what Slater Determinant is, you can just approach some people in the conference and tell like what Slater was talking in person about it. We are touching the history. Huh? Please. Huh? I wasn't checking, but there is a Wikipedia site that you can check. Okay, so here is the brief review what we were doing in the lab. So we were choosing a model to apply our skills, and since we want to see some relation between structure and properties, we were setting up several models of linear chain of titanium dioxide from 1 to 5 atoms and oxygens attending in appropriate way. There will be important to set up directories in an organized way. It is what was the primary task. The computation is secondary. Primary is to organize directories. And since we are going to try same model with different methods, it's a good idea to think ahead and maybe arrange several directories for models and then duplicate them with, like, same model, different method. And, for the first attempt, we were doing just molecular mechanics, the simplest way, and we were recording optimized geometry image, total energy, distances, angles. And here is an example for one of those models. So in Gauss view, oh, okay, I'm happy to see SDSU. Do you hear me?
Yeah, we can hear.
Okay, so this is specifically for you. You were asking what we were doing in the lab.
Okay.
Here
yeah.
I'm briefly showing.
Okay, thank you.
Okay, so we were composing several models of titanium dioxide, then running optimization of geometry with molecular mechanics, and then in Gaussian there is a menu, pop-up menu that shows analyze results. When you click on this menu, there appear this window, and most important thing, there is total energy. Look on it and record it. Then also you can look on the optimized geometry. Personally, I like to funnel the geometry from Gaussian and Gauss view to JMOL, but you can do whatever you like. And then there are options to measure distances, angles, and it is interesting to record them because later we will be doing similar things with different methodology, and we would like to check whether different methods are diverging in results.
Yes. How to measure? Excuse me. Can I ask a question?
Yes.
How to measure the distance between two atoms? Is there in menu or where? Measuring distance and angles.
If you are modifying distance, simply in Gauss view, you do see a bar menu that you can move forward and back, but if you do not move it, but look on the value near this bar, it shows the distance or angle.
Oh.
It is the simplest way.
I was trying to do like the same one. Here you can on that picture I can see the angle and distance of bone. How you make that?
In JMOL, you click on measure.
Okay.
Distances, and then you need to click for selecting a pair of atoms or 3 atoms or 4 atoms for the hero.
It's on
then
JMOL.
They all are summarized in the same image, which is better for visualization.
And in my simulation, I got different energy, total energy than this one. The one that you had.
Do not worry.
Okay.
Just record what you have, and we will analyze why it is diverging later.
Okay.
Okay. So here is the plan. So we are going to briefly review what we were doing in the previous part of the course, and then our goal is to focus on total energy. So you can sit and relax. I will be repeating things that we already know for a couple of minutes. So the oversimplified procedure of all computational chemistry is to have something in and have something out, right? So we're preparing atomic models, feeding it into code with some software, and getting some observables and geometry, right? And for principles of software, one can understand that when there is atomic models that composed of position of ions and several electrons, where positions of electrons are not specified because they move so quickly. And we did apply multi-hour effort to split the equations that control the behavior of ions and control the behavior of electrons. So we do have electronic part and we do have ionic part. So up to now we were postponing the electronic part and focusing on the nuclear part, and we agreed that with certain approximations in the classical limit, when ions are heavy, temperature is low, there is no reactions, one can control them with Newtonian equations of motion. And those Newtonian equations of motion allow to find optimal geometry by browsing across potential energy surface. So the dependence of total energy of system for a given electronic state as function of nuclear configuration, as function of position of atoms. And what is most important and what is typical task that simplest and typical task that codes are doing, they're finding global minimum, the lowest point on the potential energy surface. By the way, if one tries to find it mathematically, which is not appropriate here, one can try the first derivative equals 0 and second derivative of potential energy surface larger than 0. Right? So if you find a point that satisfies these two conditions, it will mean that you have minimum, at least a local. So we do not know the whole surface because it is too heavy computationally. And we are using an algorithmic approach to browse, to navigate through this configurational space and find optimal geometry. So we are finding the potential energy surface only at specific points, and then we are computing so-called gradient, the derivative in respect to change of position. And this gradient is prompting us the direction where we want to go. It is our compass, where we want to go into the space, in this configurational space. And if we increment the nuclear configuration according to this gradient, then through several iterations, we are achieving the minimum and providing an output of optimal geometry. And in your homework number 4, you will try to repeat these calculations by hand for simplest model with a little bit different conditions in respect to previous work. Okay. So we were dealing with ionic part. Now it is time to switch back to the electrons. And in order to talk about electrons, we are making any possible approximations about ions. So we forget that they are quantum particles. We forget that they have distributions and potential energy surfaces. They're just parameters. Some values, just nailed down positions of ions. And for 12 lectures, we do not believe that they can move. So they're just centers of attraction. So ions are fixed, but electrons can do whatever they like. Anything? Ions are so here I'm just copy pasting of what we were doing on lecture number 2. So since we are doing this formal treatment, we are trying to comprehend how the codes are working. We are writing down this formal stuff, the operator of energy, and we were agreeing several lectures ago that total energy is composed of nuclear and electronic parts, so kinetic energy of nuclei that we do not need right now. So we we are forgetting about it. Kinetic energy of electrons that we take into consideration for today and next 12 lectures. Then interactions of nuclei to each other, we also do not need it. And then we have interaction of electrons to ions, attractive interactions. So here are those positions that we are not going to modify. Here are the nailed down positions of ions. So they attract electrons. And there is also a next bad guy who makes our life difficult, the interaction of two electrons to each other. So this term will attract additional attention. So we have 1, 2, 3 terms, and they are entering the Hamiltonian for electronic part. Kinetic energy of electrons, attraction by ions, and repulsion between electrons, right? So two electrons do not want to stay close to each other. And we are going to solve this equation. So it is our goal, our task. Well, no one of us is going to solve it. Computer is going to solve it for us, but we are going to set up right directions, right task for software that will be solving this equation for us. Okay. So as soon as we solve this equation, we do have a positive outcome. We do have a energy of electronic subsystem, which here comes up as a eigenstate. But this part is naturally entering the geometry optimization. So now we appreciate what it is and why we need it. Because in our algorithm of geometry optimization, we need to compute the total energy for each nuclear configuration. And we were skipping understanding of this process for some time. Now we are going to focus on it. It is a major task. So knowing this energy for different positions of ions can be incorporated into the code for the purpose of geometry optimization. This motivation. Well, if you go to the library and open an arbitrary book on computational chemistry, most likely they will consider this equation only. They will skip geometry optimization at all, especially if it is a 40 years old book. So we agree on that, and our task is to find energy and wave function of many electron systems with several attraction centers. Okay. Is it easy or it is difficult? So what are our challenges? What should we do, or what we shouldn't do? What to avoid? Well, there is a fact that we cannot change, that most molecules and materials have too many electrons. So we are approaching same challenge as we always do. So the number of variables is big. We are trying to solve for function that depends on many variables. And even if we are humble, if we understand that it is not possible to solve it analytically, mathematically, if we are targeting numerical solutions, still it is very challenging. So same analysis as we did on last lecture. So suppose that we can fit one-dimensional function with maybe 10 grid points, values for 10 different values of the coordinate, right? Then if we have 3 dimensions, x, y, and z, then to represent 3-dimensional function, even in the approximate way, we need 10 times 10 times 10, 1,000 values, which is okay. One can do it on a cell phone. So hydrogen, the system with single electron, it is like hydrogen atom, helium ion or lithium doubly ionized ion. If you go for a little bit more, a little bigger system, the size of our wave function starts to grow, and this growth is very dramatic. It is challenging. So if we take just 2 electrons, the number of grid points will be million, which is also okay. So H2 molecule can be computed precisely. If you just try to take one isolated carbon atom with 6 electrons, then it will be 3 10 to the power 3 for each electron, and here 6 is number of electrons. So we have 10 to the power 18 just to have a wave function of a single atom, which is not hydrogen, multi-electron. So it is already a little challenging, and I doubt that it is practical. But if the government agencies support this research, or if it is a like nuclear energy research, probably it is possible with on the top edge of the computational facilities. But as soon as we try to do some simple organic molecules, then we have 6 times 2 electrons, and 2 electrons come from hydrogen, so 14 times 3 will be 10 to the power 42. This will not be possible for a long year or a long time to compute in the explicit form, even with powerful computers, even with low precision. So the total wave function is not possible to know. So we need some tricks, we need some approximations. We need to know what we can neglect in order to predict the properties of the natural systems in a more or less reliable way. Okay, so we are not the first people on the Earth who are trying to solve mathematical problem where one needs to find function of several variables. This type of problems was known for a long time. And the typical philosophy is, as we were already practicing, can one reduce the number of variables? Can one separate them? Can one think that there are some parts of systems that do not interact to each other, and the function that we are solving for can be factorized on some independent factor? So can it be factorize solution? Well, if it would be possible, maybe with some approximation, if it would be possible, then the very appetizing approach is to solve equation only for one electron with some maybe additional terms into equations, and then compose this multi-electron wave function as a product of one electron functions, which is very possible. But this simple idea to establish product of multivariable function as several one-variable functions is not straightforward. It is desired. Everyone understands that it is very beneficial. Everyone wants to do it, but there are objective difficulties. So we are going to slowly address them, and basically it is what computational chemistry is doing. So if we want to formulate task of computational chemistry in mathematical language, it is the reliable way to represent multi-electron wave function as a product of single electron function. Please. Let both, starting from just hydrogen atom one ion, one electron, and then looking onto several ions but one electron. Okay, so we can probably partition our plans, our goals, our effort onto three categories. We can find those single electron functions which can be helpful later with our philosophy to use them as building blocks for total solution. So we need a procedure that helps to compose the wave function out of these building blocks. And then we need to be very careful to see what are we missing if we're building products or some combination of products. And this is like biggest part that is not solved, but there are several researchers who design better and better methods to address this challenge. So single electron compose products and then take into account the interaction of electrons. Electron to electron. I think I'm just copy pasting the same. Yeah. For the first, we are focusing on hydrogen atom to form our building blocks. So for the second, there is a concept of so-called Slater determinants. And for the third one, we will address it later. There are several ways, and it is major. It is the core part of the course, how to address electron-electron interaction. Okay, so here you see a photograph. So it is a Dr. Ivan Mikhailov, who was part of the group and part of our department and university a couple of years ago. So he was substituting this lecture number 9 3 semesters ago, and I'm using part of his slides that he was preparing and just acknowledge his contribution. So what he was showing here, he put together the kinetic energy of electrons. And he was forgetting about intentionally forgetting about the positions of ions. No, he was not. This so abbreviated. R I sub A, and his notation stands for distance between electron and ion number A. Okay, so this term was for potential energy of electrons attracting to nuclei, and this term is for potential energy of electrons interacting to each other. Nothing new. We already discussed this. 3 terms in the energy operator for electronic systems. And I think each of us can close all textbooks and reproduce this equation, hopefully. Now, the approximation is the same equation, and next step is for a short time, temporarily, one can assume that electrons do not interact with each other. And this is very strong approximation. It is not practical. It is just only methodological. And therefore, Dr. Mikhailov used the word rude. It means very approximate. So in case electrons do not interact with each other, then even if system has many electrons, each of them doesn't feel what others are doing. And each of electrons can be considered as if there is also single ion, then each electron does behave as an electron in hydrogen atom. If one neglects electron-electron interaction, then each electron exactly reproduces the solution for hydrogen atom, and we just build up product of those. Each electron produces trends. Well, not just trends, actual behavior, precise behavior of hydrogen atom. And then it is a part of other courses, the wave function of electrons in hydrogen atom in central field when electron is attracted to one center, flying around and building, since it is a distribution, some shapes that all chemists know as an alphabet, right? So those S, P, D orbitals, those are coming as a solution of electronic problem for single ion. And here is their form. They are specified by quantum numbers. Principal, orbital, and magnetic, right? Each of you can present this part in a perfect way, right? And those quantum numbers determine the dependence, three-dimensional dependence of this, of those shapes, of this, those one-electron wave functions. And it is one of the few quantum problems that do have exact solution. It is not very simple in its shape, but it is written down with precise formulas. So it is factorized on the dependence on distance from center and on the angles. And there are known mathematical functions for radial part, and there are known functions for dependence on the angle. We are not going to solve it. We accept that someone has solved it for us, or we did it in other course, and now we are just utilizing the fact that solutions of a single electron around single ion are known. Here are examples of those dependence on angle. There are orbital and magnetic quantum numbers that determine those shapes, and the bigger those numbers are, the bigger number of nodes and lobes as a function of angle are. And you recognize here the S, P orbitals, right? And if you go higher up, you have this D orbitals and a little exotic F orbitals, which have maximal number of nodes and lobes. Here is the dependence on the distance from the ion, and for S orbitals it just increasing. For the simplest S orbital, for the next S orbital it has a minimum, then rises back. And here is the example for radial dependence of P orbital, which has a 0 when electrons probability to find electron near the attracting center is 0. And one can build those functions according to the formula for each quantum number. So those atomic wave functions centered around ions can serve as building blocks. So by multiplying several of those functions, depending on different arguments, because if there are more than one electron, they will depend on different arguments, will hopefully form the wave function for many electron systems. Okay, so now we do need to be a little bit more formal and set up rules that help to compose solution, multi-electron wave function, out of this single electron building blocks. And those rules are not straightforward. There is a little difficulty because electrons are strange things. They follow some quantum rules, quantum statistics. They do not like to sit at the same state at the same time. And there is a mathematical way to represent it. This Pauli exclusion principle that electrons do not like to stay in the same state can be reflected in a mathematical way, and this mathematical way is summarized in a procedure which helps us to build multi-electron function out of single electron building blocks. So this procedure is referred to as Slater Determinant, and it does reflect this specific quantum properties of electrons. Let me briefly mention what those rules are for now, and then we will spend the whole next lecture trying to understand where they are coming from, because it is a like separate subject. So, in case, yes, please. Those are arguments, independent arguments for two independent electrons. So for simplicity, we are considering example when the system has only two electrons. Okay, and we are looking how the two electron wave function can be composed of one electron wave function in such way that it will satisfy all strange quantum properties of electrons. Yes. One. Okay. And electron 1 takes, I don't know, some one function, and electron 2 maybe is taking different function. And we want to make a composition of two electrons in two different states. So the rule is that one needs to build such combination of products that will change the sign if the order of electrons is swapped. And we are going to prove it in the next lecture. Now it is just a rule. So if the electrons are swapping their position of their index, their order, then the sign of the overall wave function is changing. And with a single product, it is not possible. Therefore, one uses summation of several products in order to satisfy this antisymmetry, the swap of the sign. Sign as alternation. Yeah. First electron, second electron, one function, another function, and one builds this composition. So wave function changes sign, but doesn't change the shape, which means that any observable computed based on wave function with swapped electrons will be completely the same. So one cannot recognize where was the first electron and where was the second one based on any real-world observation. So there is some reflection of this property in the way we construct wave functions. And if by the chance we would like to put all electrons into the same quantum state, then we will get 0. which reflects the Pauli exclusion principle. If by crazy instance electrons decide to stay in the same state, there will be zero probability to find it. Not possible. So why we are speaking Slater determinant while it is just a sum of product? Because there is a simple mnemonic rule how to compose them, and it is one of the typical tasks in homeworks. I wasn't preparing the next one, but it is typical in many courses. Like you are given such and such functions, you have so many electrons, please compose Slater determinant. So one arranges functions going horizontally along the rows, and one arranges the electrons going along the columns, and just put functions and electrons in a matrix, and then follows the algebraic procedure of finding determinant. This procedure automatically includes swapping of the sign, and therefore it is very simple, natural way to construct multi-electron wave functions out of single electron building blocks. Okay, so in order to believe that this formula is correct, we will need an additional effort. We will spend a little time justifying it and checking if it is truth forever or for any situation, or maybe only for ground state. And then we will keep developing the way to build such one electron wave functions that in part include multi-electron properties. And then composing the whole solution, we will be finding the way to find multi-electronic wave function. Generally, it must be matrix. There are some cases when one can simplify it. Okay, I think it is enough for today, but I'm happy to stay and answer any questions.
Dr. Gillen,
yes.
Can you explain me the non-adiabatic coupling one more time?
Yes. NA for non-adiabatic, it doesn't mean not applicable. So the total wave function for a molecule, molecular wave function, we need to build some figure with psi very big. Generally is composed as a superposition of electronic wave functions that we are solving and will be solving for a dozen lectures with some coefficients. Those coefficients, at the same time, they play a role. They can be treated as wave functions of nuclei, depending on the probability amplitude distributions for ions. The probability to find ion a little further, a little closer. So this summation of products is correct, but it is not comfortable. It makes all problems too difficult. And the natural wish is to simplify this equation into the form just of product I of R times phi of r lowercase. So the non-adiabatic coupling and Born-Oppenheimer separation tells in which limit one can go from summation of products to simply product. And it is possible in case when so-called non-adiabatic coupling is negligible. So there is an equation for this non-adiabatic coupling that connects two electronic states and makes them coupled, makes two electronic states coupled through nuclear motion. Maybe let me write it down. Couples electronic states through nuclear motion. And one can write it in this way. Of electronic function A, then derivative in respect to position of ion, then electronic function B, then you do integration, and then you multiply it by so if the derivative of the wave function, electronic wave function, in respect to change of position of an ion is substantial on one hand, and on another hand, if the momentum of an ion is non-zero, then this approximation doesn't work. So there are two components for non-adiabatic coupling. So component one, that electronic wave function is changing when we shift ions. And the second component, that ions actually do have kinetic energy. So they are, the motion has been launched. So non-adiabatic coupling makes sense only for high temperature. If everything is frozen, then it is really negligible. Momentum is not zero. So in case this product indeed approaches small values, then wave function of the whole molecule, which is a product of electronic and nuclear part, is written in this way. If it is non-zero, then one should consider more complicated dependence with summation. Does it answer the question?
Does this, if non-adiabatic coupling is zero, we can consider the, does this expression helps to like remove a nuclear effect, separate the nuclear effect and the electronic effect?
Yes. Yeah, it's a good verbalization.
Okay.
Okay.
I think I got it now.
Very good, thank you. Any other questions? Okay, if not, then class is dismissed, and feel free to stop by, write emails, communicate, and see you next week. No lab today, only on Tuesdays.
Non-adiabatic coupling. राखेर अहिले नराखेर त्यसलाई हटाएर त्यसलाई जिरो बनाएर
माथिको चाहिँ
इफेक्ट
कम्प्लेक्स
नभएको
भयो कम्प्लेक्स
न्युक्लियर
कम्प्लेक्स
इफेक्ट
भयो एरोमेटिक कपलिङ चाहिँ जिरो है तलकोमा छ सरेको होइन
नन एडिबेटिक कपलिङ सक्यो भनेपछि त्यो सिम्पल भयो न्युक्लियरबाट हटाइदियो होइन
न्युक्लियरबाट हटाएको छैन कि अहिलेसम्म समेसन अफ प्रडक्ट्सबाट प्रडक्ट मात्रै छ कहीँ आर चाहिँ नि एउटा फङ्सन भयो होइन त्यो चाहिँ नि एले इफेक्ट गर्यो त्यो त्यसले इफेक्ट गर्यो त्यसपछि फेरि भिडियो एक्सिडेन्ट पर्छ
उदाहरण जो आयोनिक पार्ट हटाउने भनेको कि आयोनिक पार्टलाई चाहिँ नेग्लेक्ट गर्नु होइन सिम्प्लिफाई गर्नको लागि आयोनिक पार्टलाई नेग्लेक्ट गर्नको
पहिला चाहिँ नन एडिबेटिक कपलिङ जिरो हुनु पऱ्यो होइन
नन एडिबेटिक कपलिङ जिरो हुनु पऱ्यो
त्यसपछि सिम्पल टर्ममा आयो फेरि हटाउँछ क्या पछि फेरि डिफ्रेन्ट प्रोसेस
अनि यसले हामीले गरेको त्यहाँ स्ट्रक्चरहरू छ नि त्यसलाई हामीले यतातिर ल्याउनु मिल्दैन केबाट ल्याउनु के फोर्टीबाट ल्याउनु
विनएससिपीबाट
निकालिस् तैँले हेर मैले त
विनएससिपीबाट फाइलहरू चाहिँ तार्नु मिल्छ होइन
विन एससिपी
मिल्छ भनेपछि सकिहाल्यो नि त
मलाई सिक्नु पऱ्यो होस्ट नेम के
कहिले बुझ्छ
पर्दैन सोध्यो भने झन् चाँडै भन्यो भने जाऊ हुन्छ सोधेन भने थाहा छैन भने त्यहाँदेखि अब सबभन्दा चाँडै गरेर बुझाइदिनुलाई 3 चाहिँ होइन अनि अरू चाहिँ 1 2 3 2 चाहिँ पहिला त्यो चाहिँ ल यहाँ हेर्न युजर hpc.usd.edu हो होस् नि किन भएन त भएन पासवर्ड यार इसेस डिनाइड भन्छ तैँले गरेछस् PC at claim पर्दैन ए सबै के पहिलाको साइड होला हेरेछ न तपाईँहरूलाई जस्तै बुझेको छ
मैले केही बुझेन
मैले बुझेको छैन
Some other meeting here, or you wanted to talk to me more?
We're done, thank you. We're just
Okay.
discussing.
Yeah.
Thank you.
You have, do you see all files on the D2L that I upload?
Yeah, we can see that.
Okay, perfect.
When is the last due date for that homework 2? We haven't submitted it. We are not sure.
Do not worry. I will, if you need, if you want me to extend the date, I will just make it longer.
Oh, okay. Few more days, I guess.
Yes, yes. I think it is. It does have few more days.
Oh, okay, no problem. Thank you. यो एउटा जेमलमा खोल्नु पर्दैन जस्तो। कहाँ हिँडिस्? कहाँ हिँडिस्? त्यो सीएचके फाइल खोल्ने हैन र यसले कुन फाइल खोल्छ यसले? लग फाइल। के भने अरे अघि नै वर्ग के प्रोग्रामबाट खोलेर हामीले मैले बिर्सेँ उतापट्टिको फाइल खोल्ने
विनएससीबाट सब भन्नु पर्ने यता भने
पक्न म यहाँ डेस्कटपमा राख्छु मैले बिर्सिन्छु मुभ एन्ड रिप्लेस कहाँनिर छ विनएससी ल धेरै गऱ्यो